Hello everyone. Today we're on tutorial 2, first year university physics, kinematics including projectiles, part 1. Kinematics is a description of motion in terms of velocity and acceleration. Okay, let's go to my notes. Begin with the definition of velocity. We'll start with the calculus definition, which is dx by dt. Those of you that haven't done calculus, you'll understand this definition at a later time. So we define velocity then as a rate of change of distance or the distance covered in a given interval of time. The formula that you'll be more familiar with is the definition of velocity as distance over time. When v is constant, this gives the exact velocity. When v varies over the time interval, the velocity varies over the time interval, then this formula, distance over time, gives the average velocity. We need to distinguish between the term velocity and the term speed. Velocity is the distance covered in a given time in a particular direction, whereas speed is just the distance covered in a given time. In other words, with velocity, we take account of the direction. With speed, we only consider the magnitude. So speed then is the magnitude of the velocity. V is a vector, and speed is viewed as a scalar quantity. We also need to distinguish between the terms distance and displacement. To see the difference, consider a person that walks from her house along a 2-kilometer route, returning to her house. The distance she walked is 2 kilometers, but her displacement is 0 since she returned to her starting point. So displacement is a vector quantity, while distance is usually regarded as a scalar quantity. Now let me just go to the whiteboard. Let's have a look at maybe if I consider some coordinate axes, it might help to understand the difference between displacement and distance. Supposing we start from the starting point and then we move along some curve. Clearly, we've walked or moved quite a distance. So the distance is some finite value. I don't know, let's call it A meters, whereas the displacement equals 0 meters. We return to the starting point. Alternatively, if we walk a certain distance or move a certain distance, then this is the distance that we have moved, but the displacement is the distance from the origin to where we stopped. And it is a vector quantity. Okay, that's the difference between distance and displacement. So back to my notes. Our next definition is acceleration. Acceleration is defined as a rate of change of velocity. This is the calculus definition. The formula that you'll be more familiar with is this one. Again, if a is constant, then the formula acceleration equals velocity over time gives you the exact acceleration. If the acceleration varies, or if the velocity varies over the time interval, then the acceleration is the formula only gives the average acceleration. Let's look at distance time graphs. The slope of a distance time graph gives the velocity. So if we look at this diagram, this gives you the distance moved in this interval of time. So if you look at the slope, it's x2 minus x1 divided by t2 minus t1. It's distance over time. And so clearly the slope then gives us the velocity. The slope here is positive. For constant velocity in the negative x direction, we have the following. This time initial position is larger than the final position. So when we subtract, this interval will be negative. The initial time is smaller than the final time, so this interval is positive, so that we see that we have a negative slope for this case. And the negative slope means that we're simply moving in the minus x direction. Okay, that's the slopes then give us velocity, either positive or negative, depending on the direction. Moving upwards in the positive direction, the velocity is positive. Moving downwards in the negative direction, the velocity is negative, as indicated by the slope. Okay, next consider a variable velocity. When the velocity varies, it's represented by a curve on the distance time graph. But here our velocity is different at each point of the trajectory, and we can find the distance at any given point by drawing the tangent to the point and then making the tangent the hypotenuse of a right angled triangle. So again, by obtaining the slope by this interval divided by this interval, we get the velocity at point A. Similarly, we get the velocity at point B. This time, we're going from a bigger distance to a smaller distance, so the slope is negative. I've drawn the vectors itself, but this triangle can be any size. It will give you the same answer. You don't have to use the exact value of the velocity, which in any case you don't know. So this triangle can be any size. And this just repeats what I have said. But again, the important point to notice is that the velocity vector is tangent to the trajectory at each point. So the velocity at a particular point is given by is tangent to the trajectory at that point. This just emphasizes the point that we can use a triangle of any size. We come now to velocity time graphs. Begin with positive constant acceleration. So my velocity axis and my time axis. My final velocity is bigger than my initial velocity. Final time bigger than initial time. So here I have positive differences. So I have my slope is equal to velocity over time, which is the definition of acceleration. So the slope on a velocity time graph gives me acceleration. With a positive slope, it means that and a positive acceleration, it means that the velocity is increasing. We come to a negative constant acceleration or a deceleration. In this case, the final velocity is less than the initial velocity. So this time my interval v2 minus v1 is negative. Again, my time t2 is bigger than time t1, so the denominator is positive. My interval delta t is positive. Therefore, my slope is negative. For a negative slope, it means the velocity is decreasing, so that my acceleration is in fact a deceleration. And we come now to variable acceleration. We can find the acceleration at any given point by drawing the tangent to the trajectory, or the curve, not the trajectory, but the curve on the velocity time graph, and we can find the acceleration at any particular point. So again, we see the acceleration varies in magnitude and direction along the curve. Special cases of distance time graphs. I think I'll do this for you on the, let me just adjust the screen. I think I'll do these special cases on the whiteboard. Let you look at it on my notes. There. And again here. Okay, let's go to the whiteboard. Okay, before going to special cases, let's look at some of the basic definitions. Let me start with a distance time graph for a constant velocity in the positive direction. My T1, my T2, my X1, and my X2. We call this interval delta X and this one delta T. The slope is going to equal X2 minus X1, T2 minus T1. The final position is bigger than the initial position, so this interval will be positive. Similarly, T2 is bigger than T1, so this interval will also be positive. So I have a positive slope. Distance over time is the definition of velocity. So the slope on a distance time graph gives me velocity. And the movement here is in the positive x direction. Okay. Now, what about a negative slope on a distance time graph? My T2 is again bigger than T1, as you would expect. But this time, my initial position is bigger than my final position. I'll draw the intervals in a moment, but let's have a look what the velocity is here. Slope equals x2 minus x1 over t2 minus t1. This is bigger than this, so this is a positive interval. But this time, this is smaller than this one, so the final position is smaller than the initial position. This gives me a negative. Let me rub that out. It's supposed to be eraser. Let me do that again. This gives me a positive interval. This time x1 is bigger than x2. The initial position is bigger than the final position. This gives me a negative interval, so my slope is negative. So a negative slope on a distance time graph gives me a negative velocity, which means that movement is in the negative x direction. Okay, that's just running over some of the basic definitions. Now let me go to the special cases. So let's clear this. Let's consider a distance time graph for a horizontal line. Now what does a horizontal line mean? Well, my initial and final positions are the same. Let me just call them x. My time passes as usual, so my final time is bigger than my initial time. Now let's have a look at the velocity. Equals the slope, x2 minus x1, t2 minus t1 equals. This is a finite interval delta t, but now since my final position is equal to my initial position, this interval is 0, giving me 0 velocity. So a horizontal line then means 0 velocity, and it means that I'm standing still. You can even see on the graph, x is not changing, because the line is horizontal. So for any value of t that I choose, the x value stays the same. So I'm just standing still. Okay, what about a vertical line on a distance time graph? Okay, let me clear this and let's have a look at a vertical line on a distance time graph. Okay, let's draw a distance time graph again. Now, what does a vertical line mean? Well, this is T1, T2, and let's just choose an interval. So now my velocity equals the slope equals x2 minus x1, t2 minus t1. This is some finite interval, delta x, but t1 and t2 are the same time, so the interval is 0. So we see that the velocity is infinite. So this is clearly impossible. Let me clear that. And let me draw a distance time graph again. Now, a vertical line means an infinite velocity, which is impossible. In fact, by Einstein's theory of relativity, the fastest speed is limited to the velocity of light. So c equals the slope, is dx by dt. So c is the fastest velocity possible. So there's always going to be a finite slope on a distance time graph, and the maximum slope is going to be the velocity of light. Physical objects can't actually move at the velocity of light. And the reason is, if you look, when we, in Einstein's special theory of relativity, which you may not have done yet, the mass of a physical object approaches infinity as its velocity approaches the speed of light. So it is impossible for a physical object to travel at the speed of light. Light itself can travel at the speed of light, and certain massless particles can also travel at the speed of light, but no physical object can. Okay, so let's move on to a velocity time graph. A velocity time graph. In this case, if we have a horizontal line, let's just see this from my notes. If you have a horizontal line, what this means is that the velocity is constant. You can see the velocity is not changing along the timeline. So if you take an interval t1 to t2, you see the velocity is the same here and it's the same there. That means my acceleration is 0 and the velocity is constant. Again, I cannot have a vertical line. Acceleration cannot be infinite. So a vertical line like this is again impossible, since this represents infinite acceleration. The mass is the same as we did for the distance time graph, which is why I'm kind of doing it fairly quickly. Another thing which you need to notice, which is impossible, is this. Let's go velocity time graph. Now supposing we have this, velocity has this value, then it changes with a corner and it becomes this value, then it changes again. What you need to understand is these things are impossible, because what this represents is a change in velocity in a single instant in time, which means the acceleration is infinite. So such corners on a velocity time graph are impossible. You have to have a curve there. Let me just rub those bits out. So when we change velocity, there has to be gradual, there has to be a curve. Then again, there has to be a curve. However, such graphs are drawn, but it should be just understood that sharp corners are approximations for a large acceleration. So if you have a very large acceleration, you can, as an approximation, represent the change as a point. But understand that, strictly speaking, this means infinite acceleration and is impossible. But it can only be used as an approximation for large accelerations. Okay, with that in mind, let's go back to the notes. We come now to another important feature of a velocity time graph, and that's the area under the curve of a velocity time graph. To see what this means, let's consider constant velocity, the simple case of constant velocity. And then we take a time interval from t1 to t2, and the velocity interval from 0 up to v2. The velocity we're looking at is actually the constant velocity v2 here, but it's this area, so it's this interval multiplied by this interval. So I take the time interval multiplied by the velocity interval, so it's delta t multiplied by delta v. The area under the curve is delta d, which is the distance covered. This comes from the formula for velocity. Velocity equals distance over time. Time multiplied by velocity is equal to distance. So we conclude then that the area under the curve of a velocity time graph equals distance. Let me say that again. The area under the curve of a velocity time graph equals distance. So that's an important thing to remember. Some examples. Here we have the area of a triangle, A, the area of a rectangle, the area of another triangle. If this interval is delta TA, delta TB, delta TC, then my velocity interval is from 0 to this level, which is some interval delta V. So my area then, formula for a triangle, base times height. Base times height, this one is divided by 2. For the triangle, again, base times height divided by 2. So we have the distance then is equal to this area. When you're considering a varying velocity, in other words, we have an acceleration which is varying, then the area under the curve still gives the distance covered, but this time we need to use calculus. We need to know how the curve varies with time, so we need to know the velocity as a function of time. Then we need to use calculus to calculate the area in this interval, and this again will give us the distance. Again, you won't understand this until you've done calculus. But this one, of course, is something that should be straightforward for you. We come now to the important constant acceleration formulae. I'm going to show you these and then derive them for you on the board using calculus. Again, if you don't know calculus, then just remember the formulae themselves, and later when you do calculus, come back to them. So let me show you the definitions in my notes, or my derivations and definitions. When I've determined the formula for velocity and for distance, if I eliminate time from these two formulae, I get my third formulae for, again, calculating acceleration or distance depending on what data that I'm given. So formula number 3 then comes by eliminating time from formula 1 and from formula 2. And I've done the proof. I'm going to show you the proof, but I won't go through it. It's for those of you that are interested. From equation 1, we make t the subject. From equation 2, I should say, we make this difference the subject and call it xf. Then substitute equation 4 into this, go through the steps, which I'll leave for you to go by yourselves. Then you'll end up with the third constant acceleration formula. But let me do the active derivation of the first two formulas on the board for you. Okay, let's begin with the calculus definition of acceleration, keeping in mind that acceleration is constant. I'm going to use another calculus operation called integration to solve this equation. So when I integrate and I follow the rules of integration, I get this. I want to find what this constant is, my constant of integration, which must come in the operation of integration. And I can find it by setting t equal to 0. So at t equals 0, I get v equals, well, this is 0, so this just equals c. I think I'll emphasize this by putting t equals 0 there. This is equal to c. And this is my velocity at time t equals 0, so this is my initial velocity. Let me call my initial velocity v0. So replacing c by v0, I get my formula, v equals at plus v0. If you haven't done calculus yet, just remember the formula and come back to it when you eventually do calculus. But if you remember calculus, or if you know calculus, then it's a very easy formula to derive. v0 equals initial velocity. So I'm going to need this formula, so let me write it at the top. Okay, let me rub all this out. Right, to calculate my next formula, I start with the definition of velocity as a rate of change of distance. So I'm assuming acceleration's velocity is constant, so I can use this formula for the velocity here. So dx by dt equals at plus v0. Again, I solve this equation using the calculus operation of integration. Following the rules of integration, I get this. Again, I must get a constant of integration, c. To find what c is, again I set t equal to 0. So at t equals 0, x t equals 0 equals c. So once again, this is my initial position, the position at time t equals 0. So I'm going to call that x0 and call this the initial position. Well, not so much call it, it is the initial position. So I can write this formula now in the form x equals a half at squared plus v0 t plus x0. Now notice in some textbooks, this X naught is left out, and the formula is written just like this. I really dislike this because it is not the full formula, it's a simplification. And the reason they make this simplification in many textbooks is because it's always convenient to choose X naught to be 0. But you should understand that this is the formula, and that this constant is chosen to be 0 as a matter of convenience. In other words, when you do problems, projectile problems or whichever problem, you define X naught to be at the origin, so you set it to 0 and then you measure distances. So although you're going to use the formula in this form, you must remember the complete formula and understand that you choose this for convenience to be 0. But this constant must be there, the constant of integration, which we interpret as the initial position. Okay then, so this is one of my formulas. This is formula 1. And this is formula 2. And as I say, if we eliminate time between these two formulas, then I get my third constant acceleration formula, which I'll write down for you. So my third formula is 2ax equals vf squared minus, well actually I'll call this v naught. I can put v, I sometimes change, sometimes I use vi, sometimes I use v naught. Quite often, especially in projectile problems, I'll use u for the initial velocities and v for the final velocities. So I tend to vary my notation a little bit. Okay, but these are our 3 important constant acceleration formulae. Back to my notes. So as I say, this one can be derived by eliminating time from the first two. It's straightforward algebra, so I'll leave you to go through it yourselves. Let me stop sharing and let me say bye-bye until the next tutorial.